So I'm Jay Medeiros, and I work with Siemens in the Digital Industry Softwares unit in what we call the CAE COE. And I'm a career finite analyst. Started out with a lot of the older pre and post processors, and currently I support all of our Simcenter suite, especially Simcenter 3D, Simcenter Femap, and Simcenter NASTRAN. So what is DDAM? DDAM is a design analysis method that was conceived by the Navy to analyze shock loadings from ordnances that might hit the water near the ship, similar to this image you see here. If you go on YouTube, you can do a search now for Ford class and see that they did a similar test, which hadn't been done in a very long time, and it's pretty dynamic video footage. So it's a procedure to determine modal shock response of shipboard equipment due to the explosion. And what they did is they developed shock spectra, and the shock spectra were put into some simple equations to derive acceleration loads. The loads were typically put in two classes. The document itself, the original document, is the NRL 1396, and it contains unclassified and publicly available coefficients to use with the DDAM method. People who do secure work, which I've never actually used myself, use the DDS 072 classified coefficients. And the important thing for people to understand is that our NASTRAN and our Femap workflow supports that classified workflow completely. You take your coefficients offline and can run them in another room and bring your non-classified design accelerations back and complete the analysis. So in the simplest terms, there's two different types of deterministic environments. There's the steady state harmonic or periodic functions and the transient functions. And shock spectra falls under that transient umbrella. And DDAM is a very specialized type of shock spectrum analysis. What they basically do in the simplest terms is they recover the response of single degree of freedom systems to discrete inputs, and then they just sum them together to form a combined response. And in the traditional sense, they've always used damping at the time that they developed the response, so that you basically would interpolate between curves in order to find the damping coefficient that you wanted to use for your analysis. So the analysis itself becomes a simple linear analysis. So here's another graph basically showing what's going on. So we have a discrete 4 Hertz sine pulse, and we're looking at those individual single degree of freedom systems responses, and then they're all summed together to produce this response spectrum curve. So DDAM uses design velocities and accelerations, which are a function of the modal effective mass, the type of vessel, whether it's surface or submarine, the mounting location, whether it's a hull, deck, or plate mounted location, and finally the direction of the forward, whether it's, from your model, you have to tell it, what fore and aft is, what vertical is, and what a thwart ship, which is across the fore and aft axis. Two different types of material categorizations as elastic and elastic plastic. Navy documentation is pretty specific about how to determine these locations, and some of these things tend to be a bit nuanced. I'm pretty sure most of the users here would have a better understanding of that, how to classify these things than I would. So basically, these are equations that are used for the design velocities and accelerations. And you can see they're basically linear equations, and the coefficients here that you see are all contained in the NRL coefficient file. Basically, what it boils down to in this second stage here is design velocities and accelerations are computed per mode, and they're generally a factor of 0.8 to 2.0 times certain reference velocities and accelerations. And this is fully described in the NRL 1396 document, which is pretty easy to find online. If you have any trouble finding it, let me know. I've got copies of things like that. The equation used to do the summation is here. It's this NRL Summed Response, and this is a snapshot taken directly from the Simcenter NASTRAN Advanced Dynamics Analysis Guide. And that portion of the document that's related to DDAM is very well done. I mean, it's complete. It's, you know, anyone who understands NASTRAN won't have any problems following. There's multiple examples of the workflow, but what you can see here is it's basically an NRL Summed Response. It's a form of a sum of the squares response. So Femap and DDAM is broken into a three-phase workflow, and I'm going to repeat this over and over again because a lot of people don't understand it. The operation is to calculate the modal fixed base normal modes and save the modal parameters. The second operation is to run the NAVSHOCK DDAM executable, which will generate these accelerations based upon the description of where the, what type of ship it's mounted on, what the location is, the forward and aft directions, as well as whether it's an elastic or elastoplastic analysis. And finally, taking the result from the DDAM executable, NASTRAN calculates the responses. Phase 2, of course, can easily be performed at a secure location. It's just a simple flat text file. Put it on a thumb drive, carry it off in the room as required, and you can run those loads offline. Now, once again, it's a little bit weird the way NASTRAN works for those that aren't familiar with dynamic analysis. You know, historically, rigid elements are used to connect the mounting location to a single grid point with a spidered rigid element. Then you create a normal mode solution, basically to check your model out and make sure things look as you expect. You create two constraint sets for doing the DDAM workflow, and this is where it gets a little strange. People haven't done that in dynamics. So you constrain the rotational degrees of freedom at the independent grid point. And then you have the second SPC set, which I always name support, just so I know how to find it when I'm setting it up. And you reference it in this kinematic support entry. As far as Femap is concerned, it's a solution 103 with a modification. You basically go into the DDAM options portion, and then it switches the solution type from solution 103 to solution 187 response DDAM automatically. And this is where this is described. You expand the DDAM section, and the minute you toggle enable DDAM, this entire form can be filled out. And if you look at this form, there's a little bit of fuzziness to it. And the one area that was confusing to me initially was the equation type. And it's because Femap supports so many different finite element codes. You know, it supports MSC NASTRAN as well as Simcenter NASTRAN, and still even NEI NASTRAN. So if you take a look at this, it's got what you'd expect. You can use the built-in codes. And if you enable built-in codes, it's going to use the NRL 1396 coefficients. The only item you do have to specify is the minimum acceleration. And here in this form, I've basically put it as 6 Gs. One other thing to note, if you model everything in inch/pound/second mass consistent units, NASTRAN is going to take care of the rest for you in terms of correcting to kip loads. So here's where you would specify coefficients if you wanted to do that. Once you toggle this specify coefficients on, hit specify coefficients, this form pops open, and you basically populate this form. And you can, if you're familiar with the coefficient.dat file, you know, all these things will look familiar to you. And this is an example of a coefficient file that was written out by Femap. Now, when you do either built-in or actually if you do user-defined or any of the other coefficients, it will actually write out a file. And I've renamed it here DDAM coefficient, but Femap's going to write it out to the DDAM to a Fortran Unit 21 file. But you can rename it and call it whatever you want, and often I will do that so I can keep track of things. So the workflow for using coefficients from an external file is almost identical. You know, you browse to where that file is located, and Femap's basically going to pass that pointer along to the DDAM executable. So here, once again, is what this coefficient file looks like. It's you know, it's not all that interesting or anything, but the one thing you do have to do is if you tend to run it offline and you're going to use this file, you have to make sure that if you call a surface deck elastic load set, that line exists in there. You can have as many of these configurations as you want. Now it's very strict and it's F8 formatted, $ comment, everything that's consistent with what NASTRAN allows. You can have multiple load sets in here too. So what I had done at one point is copied the NRL 1396 files, and I kind of use them as a template, if I want to go in and basically show how you can modify those and run your own codes, your own loads. One thing that they did finally in NASTRAN 2021.1 is they include the capability to recover equation forces. And why that's important is in the past, you would have to use coincident node Z-bush elements to recover any sort of attachment loads you might have. Now that's completely supported, and of course, because Femap supports contour vectors, it makes a very nice way to do post-processing of your interaction loads between mounted components connected with rigid elements or MPC equations. So one of the things that happens when you write a NASTRAN deck is that, there's three parts. There's the file management section is the first part, and that's where we do the assign statements of these functional files that we're going to need to run this workflow. And if you take a look at this, it looks just like any other NASTRAN you might have, except it's got response DDAM instead of super element modal solution. So there's 3 lines in here. You notice that one's an output file, and that's because NASTRAN as a first step writes the modal parameters out to that file. And the second 2 are input files, which basically NASTRAN is going to be reading from it at a later point. And describing those a little more detail, this would be the phase 1 file. The modal solution 187 writes the mass participation factors and modal mass out to a flat text file. DDAM F13 is the file that NAVSHOCK, the executable, writes to, and it writes that using the description that is written to F21. So it's, we'll talk about this a little more, so it'll be a little less confusing. Within the case control deck itself, it's a very simple case control. It looks just like a modal solution. We have a method card and an SPC card. One of the things that's always good to do is to turn on your weight check so you can see if your model looks like it's supposed to. But the thing to remember is the modes have to be mass normalized, and that is the default for Femap. So unless you change it, it's going to be proper. Another thing I do is frequently I'll request modal effective mass fraction, and that can be very useful to make sure you get the number of modes included for your DDAM analysis. And I think they recommend 80%. Inside the bulk data, I have the normal things. One thing to notice is this top card that I have commented out, D3 only. And that's a card that by default is no, and I've got it in here commented out with yes, and that's the card to include when you want to do a restart. The second card is also one of the new features. NASTRAN recently updated the DDAM process to just calculate stresses using membrane components. So it actually writes the results to the FO6 file for bending and membrane, and then a second set for just membrane. We'll talk a little bit more about that. And you can see here's where the constraint sets are written, and we basically constrain the rotation of the master node, and then also provided a support at the same grid point of directions 1, 2, 3. Now, if you just wanted to run one direction, you could specify that here and then change what your constraints are. One other card that's in here is the select mode, and we'll talk about that a little later. That's totally optional, but you can have it basically go through and run until it reaches some threshold of modal mass that you want, and then it will stop trying to find modes. So once again, response DDAM is a 3-phase process. Phase 1, calculate normal modes, modal effective mass. Phase 2 is run the NAVSHOCK program, and this is all run in an integrated fashion. So it's lights out if you use all the built-in parameters. And then phase 3 basically takes the DDAM results and then calculates the modal responses using the NRL summation method. This is an example of what the NAVSHOCK control file looks like. Femap out of the box is going to name it DDAM.f21. I frequently will rename this thing. There's an issue now related to if you do select modes, it expects the file to have a .inp suffix. So we'll talk a little bit about that, but it's a simple file, right? It's it's basically 10 lines with some strings of text, and you can see the descriptions of them here, and they're just what you'd expect. The only thing we haven't discussed at this point is the last 2 lines are force conversion factors. So if you happen to have modeled in non-inch-pound-second units, you can put in conversion factors to correct that for the DDAM calculations. And here are the basic DDAM calculations. And like I said, if you model in inch-pound-second mass units, then Femap's going to take care of everything properly, or actually NASTRAN is. It divides by 1,000 to correct it to kip mass. One of the things of the DDAM verification file, it produces this flat text file, which shows you everything that you fed in, right? It shows the force conversion factor, the minimum acceleration values, the mounting location. Basically, it's a full description of what it used to calculate the design shock values. And if you look down in this table, there's a table of participation factors, as well as the G loads that it calculated from the DDAM executable. And this is actually becomes part of the FO6 file, but it also writes it to a verification file that's basically looks exactly like this. So the restart workflow gets a little more complicated. I think at this point I'm gonna jump in and show the basic setup for the integrated workflow, because I think it'll be useful here. And what I've got is a very simple model. It's I don't even know what it is. Just someone just threw it at me. But the interesting thing about this model is it does have a very large rigid body lump mass system up here. It's a Con M2. And it represents the bulk of the system mass. So as a result of that, when you run your normal modes, it very rapidly, gets 80–90% mass participation with a very few modes. So it turns out to be real convenient for setting up an analysis like this. So we go in here under Manage, and we'll create a new analysis set, and we can run a normal modes analysis to start. And let's just do that. And we change it to. It is Simcenter NASTRAN, change it to normal modes. Basically, we're going to walk through our normal steps, and we're going to take all the defaults. One thing I'll do is I'll turn on the weight check. I'm going to just take 10 modes, because I know that's going to be plenty, because I've run this a few times. And this is where it's useful to turn these on. Modal effective mass fraction is a good one to get. And we'll use the participation factors and say next. This is where if you want to set up a normal traditional solution 103 shock response, you would set that up here. We're not going to do that. We're just saying normal modes. Oops. Say 10 modes. And I already have set up my constraints in here. So what I did is I have a fixed base constraint set. I'm just going to run that. And if I wanted anything else here, I could request that. I'm just going to take the defaults and we'll analyze that. And this thing runs super fast, so we'll get some results. And I believe it's already done. So that's how quick that was. Come in here and look at this is what I was talking about for the mass fraction. I don't know if you've ever done this before, but when you run these, you can come in here and get the modal mass sum. And this one here is pretty interesting to look at. If we do a show and charting, and basically goes across and walks through the modes and shows the sum of the modal mass. And you can see we've got well in excess of 85% mass for all 3 directions. So we got direction 1, 2, and 3 here. So it's a good check, make sure you've got enough modes, give you some confidence in that. And I'm one of the old time users here, but I'm warming up to using the post-processing toolbox, which I kind of, I pushed off on doing that for a long time. So let's go in here and look at a deformation, and we'll do a deformed shape, mode 1, and we'll just kind of walk through some modes. And this first mode is, it's a Z mode. You can see that these tabs are bending at the base, and we could walk through these. And that one turns out to be I believe a vertical mode. And actually that's the vertical mode, but all right, we get exactly what we expect. So the useful thing here is we've already run this. We can come back into analysis, and if we do manage here, we can copy this set. That's the easiest way to do it, and we'll edit it. And we'll edit it here and we'll call it DAM integrated. And what that really is going to do is it's going to use all the loads that are built in to the NRL 1396 specification. So we'll walk back through here and we don't have to do anything particular. Main thing we need to do is change our boundary conditions. So I'm going to jump down here and expand this and edit this and change it to fixed rotation 456 for our SPC, and then for our support card down here, like I said, I'm going to have a name it thing support so I don't get confused if I have a lot of constraint sets. And then we'll expand our options tab, look at DDAM, and DDAM's, there's nothing there. So we edit it, we pop the form up, and the minute we do this, all these things become available to us. And like I said, straight out of the box, you don't have to do anything other than specify the minimum acceleration in G's. That's the only item that is not fully specified when you set up the integrated load sets. And take a look at this form once again. We've got a DDAM analysis using built-in coefficients. Now, if I wanted to specify coefficients, I could check this box, hit this tab, and this form pops up, and I could populate that form with any of the load factors I want. Similarly, I could specify from an external file, and I could browse for that file here, like I have one. Let's just edit that, take a look at it. And that's exactly like it was in the presentation. It's FA left justified file, and it's very, it's very well formatted. So what I typically do was take one and use it as a template. I actually produced a spreadsheet to do the same thing, so I could change them if I wanted to there. But so actually it's ready to go. So I'm gonna change it back to use built-in coefficients. Hit OK, and let's do a preview of the deck just to take a quick look. And if you take a look here, we've got just what we showed in all the slides. And Femap prefixes everything with a full path. And it does name them F11, F13, and F21. And like I mentioned to you earlier, all this will work fine out of the box. But if you do specify select modes where you're going to try to have it eliminate mode set, different modes from the solution calculation, you will have to rename this to .imp. It's just a bug that exists now, and I want you to be made aware of that. And you would do that by saying edit preview, and you come in here and change that extension. But we're not going to do that here. Let's take a look through the deck. Looks exactly like we expect. DDAM still says no mode to the subtitle, but we have a method 1, SPC equals 1, and modal effective mass plot. And I guess actually what I want to do here is I'm going to say done, and I'm going to come in here and edit what I want for output, because I need some additional output here. So go in here and edit the output request and edit it. And I'm going to change it to, I want the equation force, which will give us our RBE2 connection loads. If I wanted velocities or accelerations, I could request them. I could say element forces and stresses. And it's useful to say print and post process. And the reason for that is if you want to get bending plus membrane as well as membrane, you can read the FO6 file in, and that's as a workaround to get both result sets in a single run. So actually that's ready to go here. There's nothing else I really need to do. I wanted to show you one other thing, I think. Let me look. Preview. There's nothing here. Yeah, Femap does something that's not, this membrane stress parameter card is not the default, but Femap had so much, the developers there had so much experience with the DDAM user community wanting that to be the default that they turned that on. But if you wanted it to get just the bending, you would basically comment that out, and that would eliminate the membrane separate calculation. So we'll hit analyze. And this also runs fairly fast. It takes a little more time, but one of the things you see is, looks like it's already blasted through there and read the results in. So if you go in here and look, we have some result file now. There's our modal results. And I'll come in here and look at the DDAM integrated results. And you can see what we've got. We've got the sum results by excitation in each of the independent directions. So let me close this back up. And if we post-process that, instead of displacements, we'll do stresses. And another thing to understand is that because we don't know the phase relationship between the loads, the von Mises stress is the only meaningful combined stress that you should be using, I guess, to determine what your stresses look like. Another thing, people don't use a lot of these filtering, so you can come in here and type in von Mises, for instance, and basically filter. And you can see I've got the plate top von Mises stress, and basically we can walk through those here just by hitting this arrow. So that's the Y direction, and then that's the Z direction. So you see, this is kind of a simple example. We can actually post-process beam von Mises stresses too. That's something that other people don't seem to know. And under the advanced post beam cross-section tool, you can actually go in and do contour plotting on the cross sections of the beams. And the nice thing there is you can turn off the bending membrane, bending components, so you just get the axial and shear related von Mises stresses. Let's jump back into the slide presentation real quick, and we'll try to move a little rapidly here because this is pretty dry. The restart workflow is pretty simple. Basically, you're going to utilize that first run to get the normal modes and save the results to that DDAM F11 file, and you have to toggle on save database for restart. So what that does is it solves the model, saves that DDAM F11 file, and the thing you have to put in there is one parameter card. Femap does not support this at this point, but we'll go down here on the NASTRAN bulk options, hit start text on, and basically enter this one line, which is param d pre only, comma yes, and that tells the DMAP to basically stop after phase 1. The next step, if you wanted to take your loads offline and run them in a secure room, is you would pop your DDAM F11 file to a thumb drive and take it in that room. I don't know what security protocol is, but that's how I would do it. And you run the executable, and from the Femap installation folder, wherever there's a NASTRAN subfolder, an ASC NAS, and then there'll be an EMT64 TNTL DDAM.exe. So I've actually set that path on my machine so I can run it basically from a PowerShell. And you can run it either one of two ways. You can run it interactively, where you feed it a file that gives the executable all the information it needs to do the run, or you can run it interactively line by line. And this DDAM is going to exe basically is going to prompt you for all the inputs. It's basically file names and mounting location and directions and things like that. So for the phase 3 portion, we take I duplicate the phase 1 analysis setup, hit restart, browse the folder where the solution is run, point to the DDAM master file. With edit the file management section, it does require one edit. And the important thing to notice here, Femap's going to write out 3 lines. The only one you need for phase 3 is the DDAM.f13, which is what was generated from running the DDAM executable file offline. The one thing you have to do is comment it out and change it to status equals old, and that's all you have to do. Another thing to notice down here, and this is the syntax that Femap uses when it does a restart. It's basically you're reinitializing the dictionary and saying I want you to completely reread the deck, and I've commented out the D pre only card so that it tells it to go ahead and continue the analysis. And it'll look a lot simpler when I do it rather than talk about it. So switching back to the model here, let's jump in and we'll jump here and manage this. And I'm gonna copy this one and I'm gonna rename it phase 1, and we'll show you exactly how to do this. And once you hit save database for restart, what that's going to do is it's going to run NASTRAN on a command line with scratch equals no, so that the dball and master files are saved. And that's all you need to know about that. Let's walk through here. And the bulk options here, we turn on I use start text only, and let's come in here and go pre only. And go param. That should be all we need. Command in here. Say okay. So taking a look at this, we'll do a preview input, and you can see it's exactly the same as what we had before. And the only thing we really have to have here is this first line, because that's what NASTRAN is going to run. It's going to run the phase 1 portion and then stop. But we can leave these others in here because it just doesn't matter. And the D pre-only card is going to instruct NASTRAN to run phase 1 and stop. So see, when I got this set up right, I can just hit analyze and it'll run super fast. And the one thing I want to look at is the very last line we see here. D pre-only equals yes, DDAM exiting, run the NAVSHOCK program manually. So the workflow for that is you'll come in here where I've got these models set up, and I'm going to right click and open a PowerShell. And if we go in this window here, I've kind of, it's a little bit of a disaster area at this point, but if we come in here and look at this folder, I've got a bunch of files in here, and this is the run we did for the restart, right? It's DDAM_sample-1. We have the dball and master. May have more in there than that. Let me look. See the date. Yeah, okay, so it's this one. That's the one we're going to restart from. If you notice, it wrote F11. In addition to that, just to make your life easier, the easiest thing to do is rename that DDAM.F11. And there's already one there, so it renamed it DDAM2. So let me clean that out and get rid of that one. Rename that. The reason why I did this, it just makes it a little easier to set things up. Inside of here, I have a DDAM coefficient file, and that's basically the one I showed you before. And I've got the defaults for all the mounting locations and everything. The second file that's important is the DDAM F21. And you see it points to DDAM F11, DDAM F13, and then it's telling it to write the output to DDAM verify. So let's see if I got, yeah, this is actually the file that you can rename .imp. So I'm going to rename it that. So I'll come in here and type in DDAM. Let me just show you how to do it interactively, first of all. Type in DDAM. So it launches the program, and the first thing it asks you is, do you want to use the built-in coefficients or use the coefficients from a file? I'm just going to say use the built-in, and I'm going to use DDAM F11 for the input file, and then it's going to write DDAM to the verification file, and it's going to write its output file, and this is the one we're going to that NASTRAN reads for the restart from to DDAM F13. File already exists to overwrite. I say yes. Then we basically define our configuration, right? Surface, deck, plastic. I'm going to take, I believe we had X and Y, I don't remember. And then is it single mode analysis or just a normal? So I'm going to take the default, and then the cutoff weight, 80%. And it writes this file. So if we take a look at that file, it's pretty readable. Let me get my notepad to open it up here. I don't know why this is taking so long. Okay, there it is. But that's basically the file that's written. So we see we have X, Y, and Z direction information that NASTRAN is going to need. So once that's done, we basically, well, I meant to do it interactively, but I'll show you that in a minute. We'll jump in here and do a manage, and we're going to copy that one, and we're going to edit it and rename it to phase 3. And we walk through here, we're going to say restart from previous, and we'll browse out here and doing it based on date. Let's see, it's this one here we want to do, I believe. Actually, it's start. And then walking through, first thing we want to do here is we can either clear this out here by commenting it, or we can do it later. It doesn't matter. I'll just do it here. And actually, it should be ready to go. So what first thing we'll do is we'll say preview input, and this is where some light editing is required. Like I said, you can see where I've commented the D pre-only out, and that's our basically reinitialize the database, have it reread the entire deck, and it's going to basically see D pre-only equals no. So I'm going to hit edit, and just to clean things up a little bit, I'm going to come in here and take out this one line, and do the same thing for this last one because we don't need it. And I'm going to change this defer to status equals old, and that should be all we need. And I could actually comment that out because I don't need that. I've already done that once. And my result requests are still the same. I got param mem stress, yes. So I'll hit analyze, and it should kick off and go. And it's already complete. So we look in here, and I have this phase 3 result set. And if we jump in there and look at it, we get, you know, basically the same results, right? They're exactly the same. And that was just run manually. The one thing I did want to point out, I kind of skipped over it, is if you want to run it interactively, if we jump out here and go into that folder where the example is, and run open our PowerShell again. The syntax is you type in DDAM space, and then you basically give it this input file, which we showed. It's Femap actually writes it out. And if I open that, and basically it's going to read that and answer all the questions that are required. So I say DDAM space DAM.inpl, and it just runs it, bang, right? It's done. It does exactly the same thing. So if you're clever, you never have to interact with that DDAM executable really, except for, you know, possibly entering that one command line. So trying to think if there's anything else. I'm gonna jump back in the PowerPoint real quick. Let's see here. Let's see. Give me a file. The thing I wanted to talk about was some of the enhancements that have been done. We kind of mentioned it, param mem stress, yes, you turn that on, the default is no, but the Femap guys have decided it's important to have that so as a default, so they've changed it. A couple other things we talked about, you know, very briefly, is the select modes card. So if you want to retain a certain number of modes, you say cell mode top and enter the number. You can say select mode %, and it will retain all modes above a certain modal weight percentage. So if you want to drop the small modes, you can do that. The other one is cutoff, which basically is going to run until it gets an effective mass level that you desire, and then basically stop calculating modes. And as I mentioned to you, there is a bug at this point, and the workaround is to rename the ddam.f21 file to ddam.inpl. And like I said, that kind of was a bug that just turned up recently. If you want to manually select modes, I've kind of validated this work for myself. Inside the NASTRAN Advanced User Guide, there's a mode select card, and you can go in and specify the modes you want to use. Like in this example here, I specify set 1, and it's modes 1 through 3, and then I have a mod select card pointing to set 1, and then you have to have a subcase. Optionally, if you want to deselect modes, you can say, you know, set up your set, and then have mod select with a minus sign pointing to that set. It'll subtract those modes from use in calculation of the DDAM response. And that's a pretty nice capability. In the past, you'd have to do some pretty heavy duty matrix partitioning and really arcane commands to do kind of the same thing. Pretty neat capability. Some new things are coming down the road. I actually have recently loaded our latest version of Simcenter NASTRAN, and it's 2021.2. And they've done some things to help the workflow for the DDAM user. And one of the things they've added is something similar to what competitors have, is a DDAM control file. And that file fully automates things. You know, if you use integrated loads, you don't have to do anything other than either use the support RBE connection or this new card they've come up with, which is an SPC dir card, which defines the directions of the excitation at the SPC locations. Now, if you're going to use RBE2 elements for your support locations, you have to have a mass there. It won't work with a massless node. So, but it is nice now because the NASTRAN deck itself is fully documenting what you've run for this DDAM CTR file. And the online docs for DDAM, like I said, are excellent. And I highly recommend, you know, consulting them on all these commands and how they're utilized. Femap, like I said, doesn't support these as of yet, but it's coming. I guarantee it'll be out in the next year's release, which they're working on right now. Another thing is enhanced solver performance. Because we do everything through DMAP, it's a little bit arcane and doesn't necessarily run as fast as it could. So they're actually taking a look at possibly integrating the results calculation by generating an OP2 based post processor. So it's a lot of good things coming. Does anybody have any questions? Let me take a look. Yeah, the video will be posted. The SDA folks are gonna do that. I'm going to try to create my own like little separate simple video that just shows the two workflows, because so many people have asked. Like I said, if you take a look at the, let me show you that real quick. I've actually got it open, I think, here. Where is it? There it is. Yeah, it turns out they did a super nice job. This is actually version 2021.2 documentation. And if you jump in here and look at the DDAM, let's see, where is it? Where is it? There it is. So the DDAM section is, like I said, it's excellent. It's very complete. So it's in the NASTRAN Advanced User Guide. And if you just search for DDAM, it'll bring it up, and it talks about the three-phase workflow. This one here is for 2021.2, so it becomes a little bit, it's a little more complicated and includes methods not directly supported by Femap. But if you look at the version that you have, you'll be able to see everything you need to do. It talks about unit conversion, what the coefficients are. Beginning this version, it actually has, that low definition card that goes in the deck. It's a native part of the deck. There's a select mode card. There's a, let's see, I'll actually have that there. If you wanted, it has examples of the external coefficient files, shows the formatting. So it's probably the most, some of the best documentation I've seen recently on a new capability. Are there any other questions? If not, I will wrap it up, but I just want you to know that if you'd like to get in touch with me, you can basically reach me at this email address. Oops. If you want to jot that down or give me a call, and I'll be happy to answer any other questions you might have. If there's any capabilities that you feel like you need to get, then let us know that too, because we're trying to chase down all the capability gaps that we have. Okay, if there's no more questions, I guess we'll adjourn. Thanks for calling in.